Somewhere in the vast darkness of the universe, there are stars so large that our sun would vanish inside them without a trace. Not shrink, not compete, simply disappear. When we look up at the night sky, the stars seem small, distant, almost fragile. But that is an illusion born from distance. In reality, some of these objects are cosmic monsters, behemoths of plasma and gravity so immense that they stretch the limits of what physics says a star can even be. But here's the real question. Is there a largest star in the universe? And if so, what would that even mean? Because measuring a star is not as simple as placing a ruler across its surface. Some stars are stable spheres. Others are unstable, bloated, pulsating giants. Some are so luminous that their outer layers are barely held together by gravity. And some are so massive that they are constantly shedding material into space, like a cosmic storm that never ends. In recent decades, astronomers have identified candidates that push the extreme boundaries of stellar size. Red hypergiants so vast that if placed at the center of our solar system, their surfaces would swallow Mercury, Venus, Earth, Mars, and even Jupiter. These are not just big stars, they are stellar behemoths. Names like UY Scuti, VY Canis Majoris, and Stephenson 2-18 have entered scientific discussions as potential record holders. But even here, things are not simple. Their size depends on how we define their surface. Their atmospheres are diffuse. Their outer layers expand and contract. And our measurements rely on light that has traveled thousands of light years to reach us. So the largest star might not be a fixed object at all. It might be a moving target. And beyond that lies an even deeper mystery. Is there a theoretical limit to how large a star can grow before it tears itself apart? At some point, radiation pressure pushes outward with such intensity that gravity can no longer contain the star's outer layers. At some point, fusion becomes unstable. At some point, the behemoth collapses under its own weight, ending its life in one of the most violent explosions the universe can produce. But until that moment, it exists as a cosmic titan. In this documentary, we will journey to the most extreme stars ever observed. We will compare their sizes to our sun. We will explore how astronomers measure something so unimaginably distant. And we will confront the possibility that even the largest known star today may not hold the title forever. Because the universe is vast, and somewhere out there may be something even bigger. When we ask whether the universe contains a larger star, we are really asking something far more complicated than it sounds. We imagine a simple ranking, a list where one star sits at the top, clearly bigger than all the rest. But the universe does not like simple rankings. It prefers ambiguity, uncertainty, and extremes that blur into one another. To understand what largest even means, we must begin with something familiar, our own sun. The sun is an ordinary star, a yellow dwarf. It has a radius of about 696,000 kilometers. If you could line up 109 Earths across its diameter, they would just barely stretch from one edge to the other. Its mass dominates our solar system. Its gravity binds the planets in orbit. Its energy sustains life on Earth. And yet, on the cosmic scale, the sun is modest, almost small. There are stars that dwarf it so completely that comparison becomes abstract. If the sun were replaced by some of the known red hypergiants, Earth would not simply orbit closer. It would not burn. It would not evaporate. It would already be inside the star. The first category of stellar giants we encounter are red supergiants. These are stars that began their lives with much greater mass than the Sun, perhaps 10, 15, or 20 times as massive. Massive stars burn through their nuclear fuel far more quickly. They shine brighter, hotter, and more violently. But their brilliance comes at a cost. They age rapidly. As hydrogen in their cores runs out, their internal structure changes. The core contracts under gravity. Fusion begins in surrounding shells. The outer layers respond by expanding dramatically. What was once a hot blue or white star swells into a bloated red giant, hundreds or even thousands of times the Sun's radius. One of the most famous examples is Betelgeuse in the constellation Orion. Even with the naked eye, we can see its reddish glow. Betelgeuse is roughly 700 to 900 times the Sun's radius. If placed at the center of our solar system, its surface would extend beyond the orbit of Mars, perhaps even approaching Jupiter. And Betelgeuse is not the largest we know. Beyond red supergiants lie the true behemoths, red hypergiants. These are among the rarest stars in the universe. They are unstable, extreme, and nearing the end of their lives. Their outer layers are so loosely bound that they drift away into space. Their atmospheres are vast, turbulent, and difficult to define. Measuring their size becomes a problem of interpretation. Where does the surface actually begin? UY Scuti was once widely considered the largest known star. Located about 9,500 light-years away in the constellation Scutum, it is estimated to have a radius roughly 1,700 times that of the Sun. Imagine placing UY Scuti in our solar system. Its photosphere would engulf Mercury, Venus, Earth, Mars, and possibly reach close to Jupiter's orbit. But even that is not the end of the story. VY Canis Majoris, another red hypergiant, was once thought to be even larger. Earlier measurements suggested it might exceed 2,000 solar radii. Later revisions adjusted those numbers downward. The difficulty lies in observation. These stars are so distant and surrounded by thick envelopes of gas and dust that their boundaries blur. We are not measuring solid surfaces. We are interpreting light. Then came Stephenson 218, a candidate that may be even more extreme. Estimates suggest it could reach over 2,100 times the Sun's radius. If those numbers hold, this star would stretch nearly to Saturn's orbit if placed in our system. But here is where the uncertainty grows. These measurements rely on stellar models, brightness, distance calculations, and assumptions about temperature. Change one parameter, and the estimated radius shifts dramatically. And because these stars pulsate, expanding and contracting over time, their size is not fixed. The largest star may literally change size over decades. So perhaps we must redefine our question. Instead of asking which star has the greatest radius at a single moment, we might ask, what limits how large a star can become? The answer lies in a battle between gravity and radiation. Inside every star, gravity pulls inward, compressing matter. Fusion in the core pushes outward, generating radiation pressure. For most of a star's life, these forces balance. But in extremely massive stars, radiation pressure becomes immense. As the star grows brighter and hotter, photons exert force on the outer layers. At some point, that outward push becomes so strong that it begins to overcome gravity. This is known as the Eddington limit. Beyond this limit, a star cannot remain stable. It begins to lose mass rapidly through powerful stellar winds. Material streams away into space. The star sheds its outer layers. It becomes unstable, fluctuating in brightness and size. In other words, there is a ceiling, a maximum size dictated by physics. Yet the universe always seems to approach that ceiling. Some of the most massive stars known are not necessarily the largest in radius. In fact, the most massive stars are often smaller in size, but extraordinarily dense and luminous. Stars like R136A1 in the Large Magellanic Cloud may contain over 200 times the mass of the Sun, but they are not swollen red giants. They are hot, blue, compact titans. This reveals an important distinction. Mass and size are not the same. The largest stars by radius are often not the most massive. Red hypergiants are bloated because their outer layers are expanded and diffuse. Their density is incredibly low. If you could somehow place a fragment of their outer atmosphere into a laboratory, it would be thinner than the best vacuum we can create on Earth. They are vast, but fragile, and they are temporary. These hypergiants live fast and die violently. Their lifespans are measured in millions of years, a blink compared to the Sun's 10 billion year life. Eventually, their cores collapse. The result may be a supernova, one of the most energetic explosions in the universe. In some cases, the collapse forms a black hole. The Behemoth does not grow forever. It implodes. So is there a larger star? At this moment in time, astronomers can point to candidates. Stephenson 2-18 may hold the current record, but that record depends on measurement techniques that continue to improve. New instruments, new telescopes, and new methods of interferometry may reveal even larger stars or revise existing estimates downward. And then there is another possibility. Perhaps somewhere in a distant galaxy, beyond the reach of our current instruments, a star exists that surpasses all known examples, a hypergiant so immense that its outer atmosphere stretches to unimaginable scales. The universe contains hundreds of billions of galaxies. Each galaxy contains billions of stars. Statistically, extremes must exist, but whether we can see them is another question. Even if a larger star exists, it may be obscured by dust. It may be too distant to resolve. Its light may blend with surrounding stars. We are limited by the tools we have, tools that grow more powerful each decade, but are still bound by physics and distance. The search for the largest star is not merely about size. It is about understanding the limits of matter under extreme conditions. It is about how gravity shapes luminous plasma. It is about the final stages of stellar evolution, when a star swells to enormous proportions before collapsing in catastrophic death. And perhaps most importantly, it is about perspective. When we speak of a star 2,000 times the radius of the Sun, the number becomes abstract. But imagine this instead. If you traveled outward from the center of such a star at the speed of a commercial jet, it would take you years to reach its surface. The scale defies human intuition. Yet even the largest known stars are small compared to galaxies, and galaxies are small compared to clusters, and clusters are small compared to the observable universe. In the end, the largest star is a reminder of two truths. First, the universe allows structures far beyond our everyday experience, objects so vast they stretch our imagination to its limit. Second, even the greatest behemoths are temporary. They are not eternal giants. They are stages in a cosmic life cycle. And somewhere, right now, one of these enormous red hypergiants is nearing the end of its expansion. Its core is collapsing. Its fusion is faltering. And within perhaps thousands of years, a blink in cosmic time, it will explode, scattering its elements into space. From those elements, new stars will form, some small, some massive, and perhaps one even larger than anything we have yet discovered. If we want to understand whether a true largest star exists, we need to step deeper into the physics of how stars grow, evolve, and ultimately destabilize. Because what we casually describe as big in astronomy is not a single, simple property. It is the result of temperature, luminosity, mass loss, internal pressure, and time, all interacting in delicate, violent balance. To begin, we must travel back to the birth of massive stars. Stars form inside vast molecular clouds, cold regions of gas and dust that stretch across light years. Under gravity, pockets of gas collapse inward. As density increases, temperature rises. Eventually, hydrogen fusion ignites in the core. A star is born. For most stars, like our Sun, this process leads to a relatively stable main sequence life lasting billions of years. But for very massive stars, those born with 20, 40, or even 100 times the mass of the Sun, the story unfolds much more dramatically. Massive stars burn through hydrogen at an extraordinary rate. Their cores reach far higher temperatures and pressures. Fusion reactions proceed faster, generating immense energy output. As a result, these stars are incredibly luminous, sometimes hundreds of thousands or even millions of times brighter than the Sun. Brightness matters. The brighter a star, the stronger its radiation pressure. Photons streaming outward from the core exert force on the star's outer layers. In smaller stars, gravity easily keeps those layers bound. But in extreme stars, radiation pressure becomes almost comparable to gravity. This is where instability begins. When hydrogen in the core runs out, fusion shifts to heavier elements. The core contracts. The outer layers expand dramatically. The star cools at the surface and becomes red, not because it is weaker, but because it has ballooned outward. This is how red supergiants and hypergiants are born. But what determines how far they can expand? The key lies in hydrostatic equilibrium, the balance between inward gravitational force and outward pressure. When a massive star enters its late evolutionary stages, energy production in shell-burning layers can become chaotic. Convective currents churn violently. The outer atmosphere becomes turbulent and loosely bound. The star swells. Yet the outer layers are no longer tightly gravitationally attached. They become diffuse, almost like an extended atmosphere drifting into space. The density drops dramatically. The star's radius increases, but much of that increase occurs in extremely low-density gas. In other words, the surface of the star becomes fuzzy. Astronomers define a star's radius by where its optical depth reaches a certain threshold, essentially where the star becomes opaque to its own light. But in hypergiants, that boundary shifts. Winds carry material outward. Pulsations expand and contract the atmosphere. Dust forms in cooling gas. The star breathes. Some red hypergiants are known to pulsate on timescales of years or decades. Their radii can change significantly. Their brightness varies. Their outer envelopes are constantly reshaped by convection cells larger than entire solar systems. And here is something astonishing. If you were standing near the outer atmosphere of a red hypergiant, gravity would feel incredibly weak. You could almost float away. The escape velocity at its surface might be lower than the speed of some stellar winds already flowing outward. The star is barely holding itself together. This brings us back to candidates like UY Scuti and Stephenson 218. These stars are not solid spheres with sharply defined edges. They are enormous, unstable, puffed up envelopes of plasma on the verge of shedding themselves into space, and they are short-lived. Massive stars have lifespans measured in millions of years. Compare that to the Sun's expected 10 billion years. The most extreme stars burn brightest and die fastest. They spend only a fraction of their lives in the hypergiant phase. So when we observe one, we are catching it at a rare moment near the end. But could a star grow even larger? To answer that, we must consider the Eddington luminosity limit in more detail. This limit represents the maximum luminosity a star can sustain before radiation pressure overcomes gravity and drives strong mass loss. When a star approaches this limit, it begins shedding material rapidly. The more massive and luminous it becomes, the more violently it loses mass. There is a feedback loop. If the star tries to grow more luminous, it loses mass faster. If it loses mass, its structure changes. If its structure changes, its radius adjusts. The star cannot expand indefinitely because the very processes that allow expansion also trigger erosion. In fact, some of the most luminous stars observed, known as luminous blue variables, such as Eta Carinae, periodically undergo enormous eruptions. Eta Carinae experienced a massive outburst in the 19th century, briefly becoming one of the brightest stars in the sky. It expelled a vast cloud of gas known as the Homunculus Nebula. The star did not grow larger, it shed itself. This suggests a natural ceiling for stellar size, not a sharp boundary, but a practical limit imposed by instability and mass loss. Yet nature often surprises us. Astronomers have discovered that some massive stars may form in clusters through mergers. In dense star-forming regions, two massive stars can collide and combine, producing an even more massive object. Such mergers could, in theory, create stars exceeding 200 or even 300 solar masses. But would such a merged star grow to extreme radii? Not necessarily. Extremely massive stars tend to remain hot and compact rather than expanding into red hypergiants. Their immense gravity keeps their structure tighter, even though their luminosity is extreme. So paradoxically, the most massive stars are not always the largest by radius. This distinction is crucial. When we ask about the largest star, we are typically referring to radius, not mass, and radius is influenced heavily by temperature and evolutionary stage. A cool, bloated red hypergiant can be larger in radius than a hotter, more massive blue star, which brings us to a fascinating point. Size in astronomy is often about state, not just scale. A star might spend only a few thousand years in its maximum expanded phase. During that time, it reaches extraordinary dimensions. Then core collapse begins. The outer layers are expelled in a supernova. The star's physical size vanishes in an explosion that outshines entire galaxies. The Behemoth does not fade, it detonates, and what remains might be a neutron star only 20 kilometers across, or a black hole with an event horizon smaller than a city, from thousands of solar radii to a point of no return. The transformation is staggering. In fact, this cycle of growth and collapse highlights a deeper truth. The universe's largest stars are temporary expressions of imbalance. They are moments where pressure, gravity, and fusion align in a way that allows expansion beyond almost anything we can imagine. But those moments are fleeting. As observational technology improves, particularly with instruments like the Very Large Telescope, Interferometer, and future space telescopes, we may refine measurements of these colossal stars. We may discover new candidates. We may even find stars in distant galaxies that dwarf current records. Yet even then, physics will remain the ultimate judge. The interplay between radiation pressure and gravity sets boundaries. Nuclear fusion pathways determine how energy flows outward. Stellar winds strip away excess mass. Instabilities prevent runaway growth. There is no infinite expansion. Even the largest star is bound by laws. So perhaps the more meaningful question is not whether we have already found the largest star, but whether we understand why such stars exist at all, and why they cannot grow forever. Because the behemoths of the cosmos are not static monuments. They are unstable giants standing at the edge of collapse, and somewhere, right now, one of them is expanding to its maximum size, a swollen, turbulent sphere of plasma thousands of times larger than our sun, only to soon implode in a supernova that will forge heavy elements, scatter them into space, and seed the next generation of stars. In that sense, the largest star is not an endpoint. It is a phase, a dramatic, luminous, and temporary peak in a cycle that has been repeating for billions of years. And in the vastness of the universe, there may always be another behemoth forming, growing, and approaching its brief moment of maximum scale before gravity finally reclaims it. If we are going to talk seriously about the largest star in the universe, we must confront something uncomfortable. We don't actually see most of them. The cosmos is vast beyond comprehension. The observable universe spans roughly 93 billion light-years in diameter. Within that volume are an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. And yet, when we speak confidently about the largest known star, we are basing that claim on measurements from a tiny fraction of what exists. We are sampling a cosmic ocean with a teaspoon. So when astronomers list names like UY Scuti or Stevenson 2-18, what they really mean is, these are the largest stars we have been able to measure with reasonable confidence. But beyond the reach of our instruments, hidden by dust, distance, and time itself, there may be others even larger. The search for stellar giants is limited by physics and by light. To measure a star's size, astronomers rely primarily on indirect methods. We cannot simply photograph most stars as disks. Even with our most powerful telescopes, the overwhelming majority appear as points of light. The distances are too great. Instead, astronomers calculate radius using luminosity and temperature. If we know how bright a star truly is, not just how bright it appears from Earth, and we know its surface temperature, we can use the Stefan Boltzmann law to estimate its size. But there's a catch. To determine true brightness, we must know the star's distance. and measuring stellar distance is notoriously difficult, especially for extremely distant objects in dense regions of the Milky Way or in other galaxies. A small error in distance leads to a large error in luminosity. A large error in luminosity leads to a significant change in estimated radius, which means that the title of largest star is fragile. Consider UY Scuti. For years, it was widely cited as the biggest known star, with an estimated radius around 1,700 times that of the Sun, but later distance measurements revised its parameters downward. Suddenly, it wasn't quite as large as previously thought. Stephenson 218 then emerged as a contender. Initial estimates suggested it might exceed 2,000 solar radii. If accurate, that would place it beyond even UY Scuti in sheer scale. But even these numbers are uncertain. Red hypergiants exist in chaotic environments. Many are surrounded by thick dust shells produced by their own stellar winds. That dust absorbs and re-emits light in infrared wavelengths, complicating measurements. What we observe might not be the star itself, but its extended atmosphere or surrounding envelope. Where does the star end? Where does the wind begin? There is no clear boundary, and this uncertainty leads to an even deeper question. What do we actually mean by size? If we define size as the radius to the photosphere, the layer where light escapes, then hypergiants are enormous. But if we define it by the core where fusion occurs, the size is far smaller. In fact, inside a red hypergiant, the fusion core may be only a fraction of the total radius. The rest is a vast, tenuous envelope of plasma. It's like comparing the size of a flame to the size of the wick that sustains it. So perhaps the phrase largest star is misleading. What we are really measuring is the maximum extent of a star's outer atmosphere at a specific evolutionary stage, and that stage is unstable. Massive stars evolve quickly. In their final phases, they can undergo violent pulsations. Some expand and contract over years or decades. Others experience episodic mass ejections. Their outer layers are not static. In some cases, astronomers have observed changes in estimated radius over relatively short periods of time. The star's size appears to fluctuate. This means that even the largest star may not hold that title consistently. It might be largest today, smaller tomorrow, exploded next century. And here is where the scale becomes almost incomprehensible. If a star had a radius of 2,000 times the Sun's, that would mean its diameter is roughly 2.8 billion kilometers. To put that in perspective, if such a star replaced the Sun at the center of our solar system, its surface would extend beyond the orbit of Saturn. Saturn, the ringed giant, would be swallowed inside the star's envelope. The asteroid belt would not just disappear, it would vaporize. Jupiter, Earth, Mars, Mercury, all gone. The inner solar system would not survive as distinct worlds. They would dissolve inside a churning sea of plasma, thousands of degrees hot. And yet, even such a monstrous star would not last long. Massive stars burn through nuclear fuel at astonishing rates. Fusion of hydrogen gives way to helium. Helium fuses into carbon and oxygen, then neon, magnesium, silicon. Eventually, iron builds up in the core. Iron is the end of the line. Fusing iron consumes energy rather than releasing it. When the core becomes dominated by iron, fusion can no longer support the outward pressure needed to resist gravity. The core collapses catastrophically. In less than a second, gravity wins. The collapse triggers a supernova explosion so powerful that for a brief time, the star may outshine its entire host galaxy. The outer layers, those same layers that once expanded to unimaginable scale, are blasted into space at thousands of kilometers per second. The Behemoth is destroyed. What remains is either a neutron star, a sphere perhaps 20 kilometers wide but containing more mass than the Sun, or a black hole. The larger stars do not fade gently. They end violently. But before that moment, their immense size plays a crucial role in cosmic evolution. Massive stars manufacture heavy elements inside their cores: oxygen, silicon, sulfur, calcium. The very building blocks of rocky planets and life are forged inside these giants. When they explode, those elements are scattered across space. In that sense, the larger stars are factories, temporary, unstable factories. Without them, the universe would be a far simpler place, dominated by hydrogen and helium. But we still haven't answered the deeper mystery. Is there a true upper limit? Observations suggest that stars above roughly 150 to 200 solar masses are rare. Radiation pressure and stellar winds appear to prevent stars from growing indefinitely. Theoretical models indicate that beyond a certain mass, instability increases dramatically. Some stars might briefly exceed 250 or even 300 solar masses, especially in low metallicity environments, such as early galaxies in the young universe, which raises a profound possibility. The earliest stars, known as population 3 stars, may have been far more massive than anything we see today. These primordial stars formed from almost pure hydrogen and helium, without heavier elements to cool collapsing gas clouds efficiently. Some models suggest they could have reached hundreds of solar masses, perhaps even more. If so, the largest stars in the history of the universe may have existed billions of years ago, long before Earth formed. But those stars are gone. They lived fast and died young, leaving behind black holes and enriched gas that seeded later generations of stars. We cannot observe them directly. We can only infer their existence from theory and indirect evidence, which brings us back to the present. When we ask whether we have found the largest star in the universe, we must accept that our answer is provisional. Astronomy is a science of revision. Distances improve, data refines, instruments sharpen, the title changes. Today, one hypergiant may hold the record. Tomorrow, a distant object in another galaxy may surpass it. And yet, no matter how large a star becomes, it remains governed by the same fundamental forces: gravity pulling inward, radiation pushing outward, nuclear fusion sustaining balance. There is elegance in that. Even the greatest giants obey the same laws as the smallest red dwarfs. So perhaps the real marvel is not just how big these stars become, but how precarious that size truly is. They are not stable monuments carved in stone. They are swollen, unstable titans, moments of imbalance written in plasma and light. And somewhere, in a distant cluster, hidden behind cosmic dust, there may be a star expanding toward a size we have never measured, a behemoth on the brink of collapse, waiting to briefly hold the title before exploding into history. When we imagine the largest star in the universe, we tend to picture something solid, a defined sphere with a clear surface, a boundary you could point to and say, that is where it ends. But the truth is far stranger. The largest stars are not solid objects in any conventional sense. They are not even sharply bounded spheres. They are immense, turbulent atmospheres of plasma whose edges blur gradually into space. Their surface is not a wall. It is a region, a shifting threshold where light escapes. To truly understand these behemoths, we must look inside them. At the core of every massive star lies an engine of fusion operating at unimaginable temperatures. In stars tens of times more massive than the Sun, core temperatures can exceed tens of millions of degrees. Hydrogen nuclei are forced together, forming helium and releasing enormous amounts of energy. But in the largest stars, especially as they approach the end of their lives, fusion becomes layered. The core may fuse helium into carbon and oxygen. Surrounding that core may be shells where helium is still burning. Outside that, a shell where hydrogen continues to fuse. And beyond those layers, additional shells may ignite as the star evolves. It becomes like an onion of nuclear fire. Each layer burns a different element. Each layer produces energy that contributes to the outward pressure holding gravity at bay. But the outermost layers are not dense. In red hypergiants, the outer envelope can be so diffuse that its density is thousands of times lower than Earth's atmosphere. The star's mass is concentrated closer to its core, while its radius is dominated by tenuous gas spread over enormous distances. If you could descend through the outer layers of a red hypergiant, you would not encounter a solid surface. You would gradually move through hotter and denser plasma until fusion-driven pressures became overwhelming. In fact, if such a star replaced the Sun in our solar system, Earth might orbit within its atmosphere without immediately plunging into a solid body, because there would be no solid body to strike. You would be inside a glowing ocean of ionized gas. The scale of convection inside these stars is almost incomprehensible. In the Sun, convection cells, granules, are about the size of continents. In red hypergiants, convection cells can be the size of entire solar systems. Gigantic currents of plasma rise and fall over periods of months or years, reshaping the star's outer structure. The star is alive with motion, and that motion contributes to instability. The largest stars are not quiet. They are noisy, turbulent, unpredictable. Their outer layers ripple and pulse. Their luminosity can fluctuate. Their spectral lines shift. Astronomers observe these variations carefully, trying to refine models of their internal structure. But the models are difficult, because when a star becomes so large that its outer layers are barely gravitationally bound, small perturbations can have dramatic effects. Radiation pressure, convection, magnetic fields, and rotation all interact in complex ways. Rotation adds another layer of complication. If a massive star rotates rapidly, centrifugal forces can distort it, causing the equator to bulge outward. In extreme cases, this can enhance mass loss along the equatorial plane. Some hypergiants may lose mass preferentially in specific directions, forming asymmetric nebulae. Over time, these mass loss processes strip away huge amounts of material. This is crucial. The largest stars do not maintain their enormous radii for long. Stellar winds, driven by radiation pressure, can carry away solar masses of material over relatively short cosmic timescales. The more luminous the star, the stronger the wind. In hypergiants, these winds can reach velocities of hundreds or even thousands of kilometers per second. The the star is literally evaporating, and as it loses mass, its internal structure changes. The core contracts. The outer envelope may shrink or destabilize further. Pulsations may intensify. Eventually, the star approaches the final act of its existence. Inside the core, heavier and heavier elements fuse in increasingly shorter timescales. Hydrogen burning can last millions of years. Helium burning lasts hundreds of thousands. Carbon burning may last only hundreds. Silicon burning may last days. The final phase, iron core formation, is brief, and then collapse. The irony is striking. The largest stars in the universe do not die as large stars. When core collapse begins, the star's immense radius offers no protection. Gravity acts on the dense core, not the diffuse envelope. In a fraction of a second, the core implodes. Protons and electrons combine into neutrons. A neutron star forms, or, if the mass is sufficient, a black hole. The outer layers follow inward, then rebound in a catastrophic explosion. For a brief moment, the star becomes brighter than billions of suns, and then it is gone. The Behemoth shrinks to something astonishingly small. A neutron star only 20 kilometers wide contains more mass than the Sun. A black hole's event horizon may span only tens of kilometers, from a radius of billions of kilometers to an object smaller than a city. The transformation is one of the most dramatic in all of physics, and yet this cycle of expansion and collapse is not unique to one star. It is a natural consequence of stellar evolution in massive stars, which brings us to another question. Could stars larger than those we observe today exist under different cosmic conditions? In the early universe, shortly after the Big Bang, the chemical composition of matter was simpler. There were no heavy elements, no carbon, oxygen, or iron. Gas clouds cooled less efficiently. As a result, the first stars may have grown far more massive than stars typically do today. Without heavy elements to fragment collapsing clouds into smaller clumps, primordial stars might have accumulated enormous masses before igniting fusion. Some theoretical models suggest the first stars could have reached hundreds or even thousands of solar masses. If that is true, then the largest stars in cosmic history may have existed more than 13 billion years ago. But those stars are long gone. They burned quickly, exploded violently, and seeded the universe with heavy elements. The stars we see today are shaped by that enriched material. So perhaps the largest star is not a fixed object, but a phenomenon that depends on cosmic era. In the early universe, conditions favored extreme masses. In the present universe, metallicity, the presence of heavier elements, enhances cooling and fragmentation, leading to somewhat smaller maximum masses. But even today, extreme stars still form in dense clusters. Astronomers continue to search distant galaxies for superluminous stars, hypergiants, and extreme luminous blue variables. With instruments like the James Webb Space Telescope, we can peer deeper into stellar nurseries than ever before. We may yet discover a star that redefines our understanding of size. Yet one truth remains. No matter how large a star becomes, it is temporary. Its size is not a permanent attribute. It is a stage in a process governed by gravity and fusion. The largest stars are not stable cosmic monuments. They are swollen giants on borrowed time. And somewhere, as you read this, one of these enormous red hypergiants is nearing the end of its expansion, its outer layers drifting away, its core growing heavier, its fate sealed by physics. When it explodes, the record books will not matter. What will matter is the energy released, the creation of new elements, the shockwaves that compress nearby clouds and trigger new star formation. The Behemoth will vanish, but its influence will remain. And perhaps from the remnants of that explosion, another massive star will form, one that may briefly grow even larger than its predecessor. In that endless cycle, the universe keeps redefining its own extremes. When we talk about the largest stars in the universe, we often focus on their physical scale, their radius, their brightness, their sheer visual dominance. But there is another way to measure greatness in astronomy, not by size, but by impact. Because the largest stars are not simply enormous spheres of plasma. They are cosmic architects. Their existence reshapes their surroundings, alters entire regions of space, and ultimately influences the structure of galaxies. A red hypergiant does not live quietly. Even before it dies, it changes everything around it. Massive stars emit staggering amounts of radiation. Their ultraviolet light ionizes nearby gas, carving out enormous bubbles in the interstellar medium. Stellar winds push outward, sweeping material into shells and arcs that can stretch across light years. In dense star-forming regions, one hypergiant can dominate the environment. Its radiation compresses nearby gas clouds. Sometimes that compression triggers new star formation. Other times, it prevents it, dispersing material before gravity can gather it into new stars. So the largest stars are not just objects, they are forces. Consider the region around a red hypergiant nearing the end of its life. The star's mass loss becomes extreme. Winds intensify. Layers of gas are expelled and form vast nebulae. These nebulae glow in infrared light, illuminated by the dying star. To an observer thousands of light years away, the star might appear surrounded by a cocoon of dust and gas, a visible reminder that it is shedding itself into space. And then comes the final act. When the core collapses and the supernova erupts, the impact on the surrounding environment is enormous. Shockwaves travel outward at thousands of kilometers per second. Nearby gas clouds are compressed violently. Heavy elements are injected into space. Iron, nickel, silicon, oxygen. These are not just abstract chemical names. They are the elements that form planets, rocks, oceans, and living organisms. Every atom of calcium in your bones, every atom of iron in your blood was forged inside a massive star. Without hypergiants, the universe would lack complexity. Hydrogen and helium would dominate. There would be no rocky planets, no organic chemistry, no life as we know it. So when we ask whether the largest star in the universe exists somewhere beyond our current observations, we are not just asking about scale. We are asking about creation, because the largest stars are the ones capable of the most dramatic transformations. But there is another layer to this story, one that pushes the boundaries of astrophysics even further. Some massive stars do not end as ordinary supernovae. If a star's core grows heavy enough, beyond about 30 solar masses, the collapse may not produce a typical explosion. Instead, the star may undergo what is called a pair instability supernova. In this process, extreme temperatures in the core create pairs of electrons and positrons, reducing radiation pressure. The sudden drop in pressure triggers runaway collapse and explosive fusion of oxygen. The result is a cataclysm so powerful that the star is completely destroyed. No neutron star, no black hole, nothing remains. The Behemoth is erased. Such events are rare, but they demonstrate the extreme consequences of extreme size. And then there are stars even more massive, ones that collapse directly into black holes without a visible supernova. These are sometimes called failed supernovae. The outer layers may simply fall inward, vanishing beyond the event horizon, from a hypergiant thousands of times the sun's radius to a black hole perhaps only a few dozen kilometers across. The size difference is almost incomprehensible. This dramatic end emphasizes something important. Size in the universe is not stability. It is not permanence. It is often a sign of imbalance, a star pushing against physical limits that cannot be sustained. And yet, the larger stars are also among the brightest objects we can observe in distant galaxies. Their luminosity allows us to detect them across vast cosmic distances. In some cases, individual hypergiants have been identified in galaxies millions of light years away. But beyond a certain distance, even these luminous giants fade into anonymity. They merge into the light of their host galaxies. Their individual identities vanish, which leads to a fascinating thought. There may be stars in distant galaxies that surpass every known hypergiant in size, stars so vast that if placed in our solar system, they would engulf not just Saturn, but Uranus and Neptune as well. But they are too far away for us to resolve individually. They remain points of light in crowded star clusters. We know they exist statistically, but we cannot measure them precisely. Astronomy at its limits becomes a science of inference, and inference leaves room for extremes. The universe is 13.8 billion years old. It has had time to produce rare combinations of mass, density, and environmental conditions. In some region, perhaps in a starburst galaxy undergoing intense formation, a cloud may have collapsed into an unusually massive star. That star may have grown to extraordinary radius, and it may already be gone, the record of its existence preserved only in enriched gas clouds and distant shock waves. There is also the question of metallicity, the proportion of elements heavier than hydrogen and helium in a star. Lower metallicity environments allow stars to retain more mass because stellar winds are weaker. In the early universe, metallicity was extremely low. This suggests that ancient stars may have grown larger than modern ones. We cannot observe them directly, but we can simulate their formation using physics. And the simulations hint at extremes beyond what we see today, which means the largest star in the universe may not exist anymore. It may have burned billions of years ago. In that sense, the question, "Is this the largest star?" becomes almost philosophical. We can only speak of the largest star we have detected, or the largest star currently known. The universe is dynamic. Records are temporary. Extremes come and go. What remains constant is the pattern. Massive stars form. They expand. They dominate their environment. They collapse. And from their remnants, new stars arise. Some smaller, some massive, some perhaps pushing the boundaries again. The search for the largest star is not about finding a permanent champion. It is about exploring the limits of physics under extreme conditions. How far can fusion push outward before gravity reclaims control? How large can a star's atmosphere expand before instability tears it apart? How bright can it shine before radiation strips away its own mass? Each hypergiant we observe is a partial answer. Each measurement refines our understanding. But the universe may always hold something slightly more extreme, slightly larger, just beyond the edge of our current knowledge. And perhaps that is the most remarkable truth. Not that a larger star exists, but that the universe keeps challenging us to look further, measure more precisely, and redefine what largest truly means. When we imagine the largest star in the universe, we instinctively compare it to our Sun. We picture something similar, just scaled up, a familiar sphere of light, only bigger. But that mental shortcut is misleading. The largest stars are not simply oversized suns. In many ways, they are fundamentally different objects, operating under extreme physical conditions that push stellar physics toward its limits. Their structure, behavior, and fate are governed by balances so delicate that even small changes can transform them completely. To understand these behemoths, we must examine something that rarely enters casual discussions of star size, pressure. Inside every star, gravity relentlessly pulls matter inward. Without an opposing force, the star would collapse. That opposing force is pressure, generated by nuclear fusion in the core and, in massive stars, by radiation itself. In ordinary stars like the Sun, gas pressure dominates. The thermal motion of particles in the core produces enough outward force to counter gravity. But in the most massive stars, radiation pressure becomes dominant. Photons, particles of light, carry momentum. When they interact with matter, they exert force. In the largest stars, this radiation pressure is immense. It is so powerful that it begins to destabilize the star's outer layers. The star approaches what astrophysicists call the Eddington limit, the point at which radiation pushing outward balances gravity pulling inward. Near this limit, stability becomes fragile. A slight increase in luminosity can trigger dramatic mass loss. The star sheds layers into space. Stellar winds intensify. The outer envelope becomes turbulent and unstable. In a sense, the star is fighting itself. Its brightness, which defines its grandeur, also undermines its structural integrity. This tension explains why the largest stars cannot remain at maximum size for long. The very mechanisms that allow them to expand, intense energy output and shell burning, also accelerate the processes that strip them apart. And yet, during that brief phase, their scale is staggering. Let us attempt to visualize it properly. If we placed a star like Stephenson 218 at the center of our solar system, Mercury, Venus, Earth, Mars, and Jupiter would be swallowed entirely. Saturn would orbit within its outer layers. The asteroid belt would not exist. The Kuiper belt would be scorched by radiation from a star whose surface temperature, though cooler than the Sun's, radiates enormous total energy due to its vast surface area. But here is something even stranger. Despite its massive radius, the density of the star's outer layers would be incredibly low. In some regions, the gas might be thinner than the best vacuum we can produce in a laboratory on Earth. So, although the star is enormous in size, it is not solid in any familiar sense. The scale is spatial, not structural. This leads to a fascinating paradox. A red hypergiant can be thousands of times larger than the Sun in radius. yet contain only 10 to 30 times the Sun's mass. The outer envelope is vast but lightweight. Massive stars also exhibit extraordinary internal convection. Unlike the Sun, where convection is confined to outer layers, in some hypergiants, convection may extend through much of the star. Giant plumes of plasma rise and fall, reshaping the surface over months or years. The surface is not smooth, it is dynamic. Images of Betelgeuse, for example, have revealed enormous convection cells, each potentially spanning hundreds of millions of kilometers. These cells brighten and dim as material circulates. Now imagine scaling that behavior up to a star twice or 3 times Betelgeuse's radius. The convection cells could dwarf entire planetary systems. And this turbulence is not merely cosmetic. It contributes to pulsations, expansions and contractions that alter the star's brightness and radius. The largest stars are variable. Their size fluctuates, which means that if we measure a star at one moment and declare it the largest, we may need to revise that claim years later. Time becomes a factor in the competition for largest. Another element complicates the picture: metallicity. In astrophysics, metals refer to all elements heavier than hydrogen and helium. Stars with lower metallicity experience weaker stellar winds because metals contribute to opacity, the ability of matter to absorb radiation. Lower opacity means radiation escapes more easily, reducing the outward push on the outer layers. As a result, low metallicity stars may retain more mass over time. This suggests that in earlier epochs of the universe, when metallicity was lower, stars could grow more massive and potentially larger before instability set in. The earlier stars may have achieved sizes beyond anything we observe today, but they are gone. They burned intensely and ended quickly. What remains are black holes and enriched gas clouds. In fact, some of the black holes detected by gravitational wave observatories like LIGO are more massive than typical stellar remnants. This hints that the stars that formed them may have been unusually massive, perhaps even among the largest ever to exist. Yet even these titans obey limits. The interplay between radiation pressure, gravity, and mass loss ensures that stars cannot grow indefinitely. There is no infinite behemoth roaming the cosmos. Physics imposes boundaries, and when a star crosses certain thresholds, it does not grow larger, it collapses. There is also the matter of rotation. Massive stars often spin rapidly. As they rotate, centrifugal forces reduce effective gravity at the equator. This can enhance mass loss in equatorial regions, leading to asymmetric structures. Some stars may appear larger in one direction than another. Others may lose material in jets or lobes. The largest stars are not perfectly spherical ornaments. They are distorted, turbulent, unstable entities. As they approach the end of their lives, fusion proceeds through heavier elements at an accelerating pace. The onion-like layering intensifies. Each successive stage burns faster than the previous one. Hydrogen, millions of years. Helium, hundreds of thousands. Carbon, hundreds. Silicon, days. And then collapse. In that collapse, the enormous radius becomes irrelevant. The core's density and mass determine the outcome. A star that once spanned billions of kilometers may leave behind a black hole with an event horizon only tens of kilometers wide. The contrast is breathtaking. It is as if a mountain the size of a continent were compressed into a grain of sand. So what is the ultimate lesson from these behemoths? Perhaps it is this: size is not strength. The largest stars are not the most enduring. They are the most precarious. They represent a moment in stellar evolution when outward pressure briefly overwhelms structural cohesion, a moment when energy output inflates the star to cosmic proportions. But gravity never truly yields. It waits. And when fusion can no longer sustain balance, gravity reclaims dominance instantly. The behemoth collapses. In this way, the largest stars are symbols of impermanence. They shine brighter than most. They expand beyond imagination. And they vanish faster than quieter, smaller stars. The Sun, modest by comparison, will outlive every red hypergiant we observe today. In cosmic time, longevity belongs to restraint, not excess. Yet we are drawn to extremes. We ask whether this is the largest star because extremes challenge our understanding. They stretch our models. They push equations to their limits. And they remind us that the universe is capable of scales that dwarf human intuition. Somewhere, perhaps in a distant cluster beyond the Milky Way, a star may currently be expanding toward a size even greater than those we have catalogued. It may not hold that size for long. It may already be unstable, but for a brief cosmic moment, it may represent the maximum expression of stellar expansion. And then, as always, gravity will write the final chapter. If we continue searching for the largest star in the universe, we eventually encounter a deeper realization. The question itself begins to stretch the limits of what we mean by star. At some point, size and definition begin to blur, because stars are not isolated sculptures in space. They are embedded in environments, clusters, nebulae, dense molecular clouds, and sometimes they interact in ways that challenge simple categories. In the most extreme stellar nurseries, collisions and mergers can occur. Two massive stars can spiral inward and combine, creating an object more massive than either original star. These mergers are rare, but not impossible. In young, dense clusters like R136 in the Large Magellanic Cloud, stars are packed tightly together. Gravitational interactions can bring them into close encounters. If conditions align, a merger can produce an object of extraordinary mass. But here is where the complexity deepens. When two massive stars merge, the resulting object does not simply become a larger red hypergiant. It may become an extremely massive, hot, blue star, compact and intensely luminous. Such stars can contain over 200 solar masses, yet remain far smaller in radius than a bloated red hypergiant. So we must ask, is the largest star the one with the greatest radius, or the one with the greatest mass? Mass determines gravitational influence and eventual fate. Radius determines physical scale. The two are not identical. Some of the most massive stars ever observed, like R136A1, may exceed 200 times the Sun's mass, but their radii are only a few dozen times larger than the Sun's. They are incredibly dense and luminous, but not enormous in spatial terms. Meanwhile, red hypergiants may have radii over 1,500 or 2,000 solar radii, yet contain only 10 to 40 solar masses. They are vast, but comparatively lightweight. This contrast reveals something profound about stellar physics. The largest stars by radius are often stars in decline. Stars whose cores are contracting while their outer layers expand due to shell burning. Their enormous size is not a sign of youthful strength, but of structural instability. It is the swelling before collapse. In that sense, the larger stars are transitional objects. They represent the final act of stellar evolution for massive stars. They are not at the beginning of their lives, they are nearing the end. And during that final stage, their outer layers can expand to astonishing proportions. But what prevents a star from expanding even further? Why stop at 2,000 solar radii? Why not 10,000? The answer lies in gravity and binding energy. The outer layers of a red hypergiant are loosely held together, but they are still bound by the star's mass. As the radius increases, the gravitational pull at the surface weakens. The escape velocity drops. At some point, the outer layers become so weakly bound that radiation pressure and stellar winds strip them away faster than they can accumulate. Expansion triggers erosion. The star cannot sustain infinite growth because mass loss increases dramatically at larger radii. The outer envelope peels away. This creates a natural feedback mechanism. The more the star expands, the more it sheds. The more it sheds, the harder it becomes to sustain that size. This is why red hypergiants are often surrounded by thick circumstellar material, the remnants of their own lost mass. They are shedding themselves into space, and this mass loss also influences their future collapse. The more mass they lose, the smaller the final core becomes. In some cases, extreme mass loss may prevent the formation of a black hole, leading instead to a neutron star. The star's size at its peak does not guarantee its ultimate fate. Another layer of complexity arises when we consider binarity. Many massive stars exist in binary systems. Gravitational interactions between companions can alter mass, rotation, and structure. In some cases, one star may transfer material to its partner, increasing that partner's mass and potentially altering its evolutionary path. Could such interactions create a star even larger than solitary evolution would allow? Possibly. Binary evolution models suggest that mass transfer can create unusual stellar configurations, rejuvenated stars that appear younger or more massive than expected. But even in these cases, physical limits apply. Radiation pressure and instability remain constraints. So when we search for the largest star, we are also searching for the edge of stability in stellar evolution. There is another fascinating concept tied to extreme stellar mass: the possibility of supermassive stars in the early universe. These hypothetical objects, formed in primordial gas clouds, may have reached thousands or even tens of thousands of solar masses. However, such stars would not resemble red hypergiants. They would be extremely hot and luminous, with relatively compact radii compared to their mass. Their existence remains theoretical, though some models suggest they could have served as seeds for the earliest supermassive black holes. If they existed, they may represent the true upper limit of stellar mass in cosmic history. But again, they would not necessarily hold the record for largest radius, which brings us back to a central truth. The largest stars by radius are products of a specific evolutionary moment. They are massive stars in late stages, with cores contracting and envelopes expanding. They are unstable giants on the verge of death. Their size is not an indication of dominance. It is a symptom of transformation, and this transformation is essential to the cosmic cycle. When these stars explode, they release enormous amounts of energy and heavy elements into space. The shockwaves compress nearby gas clouds, sometimes triggering new star formation. In that way, the death of a hypergiant can give birth to future generations of stars. The Behemoth is both destroyer and creator, and here is something humbling. Despite their scale, even the largest stars are tiny compared to galaxies. A star that could engulf our entire solar system would still be just a speck within the Milky Way. And the Milky Way itself is one of billions. So when we marvel at the possibility of the largest star, we are marveling at a local extreme within an incomprehensibly vast structure. The universe contains scales far beyond even hypergiants, superclusters, filaments, cosmic voids. Yet we remain fascinated by stars because they are understandable. They are physical objects governed by equations we can write down. They represent limits we can calculate, and the largest of them represent those limits stretched almost to breaking. So is there a single, ultimate behemoth? Perhaps not. Perhaps the concept of largest is fluid, changing as measurements improve, as new candidates are discovered, as our definitions evolve. But what remains constant is this: the largest stars are unstable. They are temporary. They are breathtaking expressions of imbalance between gravity and radiation. And somewhere in the universe, right now, a massive star is swelling toward its maximum size, its outer layers trembling under the pressure of fusion within, its lifespan measured not in billions of years, but in a fleeting few million. For a brief cosmic moment, it may be the largest star in existence, and then it will collapse, leaving behind something infinitely smaller, but infinitely denser. A reminder that in the universe, even the greatest giants cannot escape gravity's final word. If we step back from individual candidates and look at the broader cosmic picture, something remarkable begins to emerge. The larger stars are not simply anomalies. They are a predictable outcome of how the universe distributes matter under gravity. Stars do not form in isolation. They are born in clusters from clouds of gas that fragment into dense knots. Some fragments gather modest amounts of material and form red dwarfs, small, long-lived stars that quietly burn for trillions of years. Others accrete enormous amounts of gas before fusion ignites, becoming massive blue giants. The distribution of stellar masses follows what astronomers call the initial mass function. Most stars are small. A few are medium-sized, like the Sun, and only a tiny fraction are extremely massive. But rare in a universe containing trillions of galaxies still means vast numbers. Somewhere, at any given moment, thousands of red hypergiants likely exist, and among them, a few may approach the extreme limits of radius we have discussed. Yet there is another variable that influences stellar size: environment. Stars born in metal-rich regions, like our own Milky Way today, behave differently from those formed in metal-poor regions. Metals increase opacity in stellar atmospheres. Increased opacity enhances radiation-driven winds. Stronger winds strip mass away more efficiently. In low metallicity galaxies, stars may retain more of their mass and potentially evolve differently. This means that the largest stars in the universe might not reside in our galaxy at all. They may exist in distant dwarf galaxies or in early universe environments where metallicity remains low. But detecting them poses enormous challenges. Distance blurs detail. Dust obscures light. In crowded stellar clusters, distinguishing one hypergiant from another requires precision measurements and careful modeling, and even then, we rely on indirect inference. There is also the question of perspective. When we say a star is 2,000 times the Sun's radius, what does that truly mean? It is an abstract number until we anchor it in something familiar. Let us attempt to imagine it more concretely. The Sun's diameter is about 1.4 million kilometers. Multiply that by 2,000. The result is roughly 2.8 billion kilometers in radius, nearly 5.6 billion kilometers in diameter. That diameter is larger than the orbit of Jupiter. In fact, it approaches Saturn's orbit. Now imagine standing on a hypothetical world orbiting such a star at a distance similar to Earth's distance from the Sun. The star would fill the sky beyond comprehension. Its surface would not appear as a sharp disk. Instead, it would loom like an endless glowing wall, stretching from horizon to horizon. The sky would never truly darken. Even at night, light scattered through its enormous atmosphere would illuminate the surroundings. But here is where imagination falters. No planet could survive in such proximity. The radiation output of a hypergiant is enormous, even though its surface temperature may be lower than the Sun's, appearing red rather than yellow. Its total luminosity is vast due to its enormous surface area. Planets in close orbits would be vaporized. In fact, many hypergiants are so luminous that their habitable zones, if such zones could even exist, would lie hundreds of astronomical units away. But even then, stellar winds and instability would make long-term planetary stability unlikely. The largest stars are not nurturing hosts. They are transient, volatile giants. And this volatility ties into a larger cosmic principle. Extremes are often unstable. In physics, systems at the edge of stability tend to shift rapidly. The largest stars operate near physical limits of luminosity, of radiation pressure, of gravitational binding. They are perched on thresholds. Consider the role of turbulence in their atmospheres. The outer layers of red hypergiants can exhibit supersonic flows. Material may be ejected in bursts. Observations show irregular shapes and asymmetries in some hypergiant envelopes. They are not perfectly round serene spheres. They are chaotic. And because their outer layers are so diffuse, external influences can have disproportionate effects. Nearby supernovae, gravitational interactions, or changes in internal convection can alter mass loss rates dramatically. In some cases, hypergiants have been observed to dim unexpectedly, as Betelgeuse famously did in 2019 and 2020. For a time, speculation surged that it might explode imminently. It did not. But the episode reminded astronomers how dynamic these giants can be. Their size, brightness, and behavior are not fixed. They evolve. Another factor that influences maximum size is magnetic fields. While less understood in hypergiants, magnetic activity can shape stellar winds and influence mass loss. Complex interactions between radiation, rotation, and magnetic fields may play roles we do not yet fully comprehend, which brings us to an essential point. Our understanding of the largest stars is incomplete. Models continue to evolve. Observations improve with each generation of telescopes. Interferometric techniques allow astronomers to resolve stellar surfaces in unprecedented detail. Infrared astronomy penetrates dust clouds that once obscured hypergiants entirely. With each advancement, our picture sharpens, but also becomes more nuanced. Some stars once thought to be record holders have been reclassified, distances have been revised, luminosities recalculated, radii adjusted. The largest star today may not be the largest tomorrow, and yet, even if we eventually identify a star that clearly surpasses all others in radius, the philosophical question remains: is there an ultimate largest star? Or is the universe statistically certain to produce something slightly more extreme somewhere else? Given the sheer scale of cosmic numbers, it seems unlikely that we have already discovered the absolute maximum. There are galaxies billions of light years away whose stellar populations remain unresolved. There are clusters hidden behind dense dust lanes. There are early universe stars whose light is only now reaching us. Somewhere among them, there may be a behemoth that eclipses current records. But even if we find it, its reign will be temporary. Massive stars live fast and die young. Their maximum radius phase lasts only a fraction of their already brief lives. By the time we detect them, they may already be losing mass rapidly, and in a few thousand years, or even a few hundred, they may be gone, which leads to a quiet realization. The search for the largest star is less about finding a permanent champion and more about understanding the limits of physical law. How much matter can gather before radiation pushes it apart? How far can fusion inflate a star before gravity collapses it? Where exactly does stability give way to destruction? The largest stars are answers to those questions. They are experiments conducted by nature on scales beyond imagination. And when they explode, they leave behind something paradoxical. From the largest structures in stellar terms come the smallest remnants, neutron stars and black holes, objects so dense that their gravity warps space-time itself. In that transformation lies one of the universe's most profound symmetries. Expansion leads to collapse. Grandeur leads to compression. The behemoth becomes a singularity, and in the endless cycle of star formation and destruction, the universe continues to produce giants, some small, some vast, some perhaps even larger than we have yet imagined. But none of them escape the same destiny, because in the end, gravity always waits. If we have followed the journey of the largest stars this far, something becomes clear. They are not simply astronomical curiosities. They are extreme expressions of balance pushed to its breaking point. But there is another perspective we have not yet explored. Scale is not only about how large a star becomes in radius. It is also about how that size feels within the structure of the universe, because even the largest known hypergiant, a star that could swallow our entire solar system, remains microscopic when compared to galaxies, clusters, and the cosmic web. And this contrast reveals something astonishing. The universe is layered with extremes. At the scale of planets, Jupiter is enormous compared to Earth. At the scale of stars, a red hypergiant dwarfs Jupiter so completely that the planet becomes insignificant. At the scale of galaxies, even hypergiants are invisible points. Let us examine that more carefully. The Milky Way is roughly 100,000 light-years across, a red hypergiant with a radius of 2,000 times. The Sun spans only a few billion kilometers. In light-year terms, that is a fraction of a fraction of a fraction If the Milky Way were reduced to the size of North America, the largest hypergiant would be smaller than a grain of sand. The largest star in the universe is colossal only within its immediate context, which forces us to reconsider what largest truly means. Within stellar physics, hypergiants represent the upper limit of how far a star can expand before instability dominates. But in cosmic terms, they are minor features. This realization is not meant to diminish them. It is meant to place them correctly within the hierarchy of scale, because the universe excels at nested magnitudes. Inside a hypergiant's core, nuclear reactions occur at subatomic scales. In its envelope, plasma flows over billions of kilometers. Surrounding it, interstellar clouds span light years. The galaxy containing it stretches across hundreds of thousands of light years. And beyond that, galaxy clusters span millions of light years. Scale is relative, and yet, for human perception, hypergiants sit at the edge of comprehensibility. They represent the largest single luminous objects we can meaningfully conceptualize. There are larger luminous structures, galaxies, quasars, entire star-forming regions, but those are collections of objects. A hypergiant is a single, coherent sphere of plasma. That singularity is what makes it powerful in imagination. But we must also confront a deeper question. Are hypergiants truly the largest single stellar objects possible? In theoretical astrophysics, there are models that predict the existence of objects called quasi-stars. These hypothetical objects may have formed in the early universe when massive gas clouds collapsed directly into black holes surrounded by enormous envelopes of inflowing gas. In such systems, a black hole sits at the center, accreting matter, while the surrounding envelope radiates energy like a star. These quasi-stars may have reached radii larger than typical hypergiants, but they are not stars in the traditional sense. They blur categories, they challenge definitions, and this returns us to the central tension in our search. To declare something the largest star, we must define what qualifies as a star. Is it powered by nuclear fusion in its core? Must it be gravitationally stable for a certain duration? Does an extended atmosphere count as part of the star? What about stars undergoing violent eruptions that temporarily expand their photospheres? Definitions matter. Without them, records become meaningless, and even with them, uncertainties remain. But perhaps the most important aspect of the largest stars is not their spatial extent, it is their fragility. Consider this paradox. The largest stars are the least gravitationally bound at their surfaces. Their immense size comes from low-density outer layers barely held by gravity. Their mass is concentrated inward. Their envelopes are tenuous. In a sense, the larger they grow, the more precarious they become. A star twice as large in radius does not necessarily contain twice the gravitational binding at its surface. Often, it contains less per unit volume. Expansion is not a sign of dominance. It is a sign of imbalance. The largest stars are swollen because their cores are changing rapidly. Shell burning drives expansion. Energy transport shifts. Pressure gradients alter structure. It is the swelling of a system nearing critical transition. And we see similar patterns in other physical systems. When a balloon is inflated beyond its optimal capacity, its surface tension weakens. It becomes more prone to rupture. When a star expands beyond equilibrium, it becomes more prone to mass loss and collapse. This pattern repeats in astrophysics. Extremes carry instability. So when we search for the largest star in the universe, we are searching for the object closest to structural limits without crossing into destruction. And that threshold is dynamic. It depends on metallicity, rotation, mass, environment, and time. Some stars may briefly expand to extraordinary sizes during luminous outbursts. Others may maintain vast radii for longer periods. But eventually, evolution pushes them forward. The core contracts, the envelope responds, and gravity asserts itself. There is something almost poetic about this. The largest stars are not permanent monuments of cosmic achievement. They are transient giants, the final bloom of nuclear fusion before collapse. They are the universe's way of testing its own boundaries. And when they explode, they do not leave behind another giant. They leave behind something small and dense. The largest stars give birth to the smallest stellar remnants. Neutron stars only tens of kilometers wide. Black holes whose event horizons could fit inside a city. The cycle compresses grandeur into density. In that transformation lies a lesson about scale. Size alone does not determine significance. The Sun, modest by comparison to hypergiants, has sustained life on Earth for billions of years. A hypergiant, though far larger, is unlikely to host stable planetary systems for long. Longevity and stability matter as much as magnitude. And yet, we are captivated by the extremes. We want to know whether the universe has produced something larger still. We imagine a star so vast that its diameter approaches that of our entire planetary system. And statistically, perhaps such a star has existed somewhere, sometime. But whether we ever identify it with certainty is another question. The universe is not obligated to reveal its extremes. It only reveals what light can carry to us across unimaginable distances. And so the largest star may remain hypothetical, or it may already be catalogued under a name few outside astronomy recognize. Either way, it stands as a reminder of the scale at which nature operates, a reminder that our sun, so dominant in our sky, is a modest participant in a much grander cosmic drama, and that somewhere in a distant region of space, a hypergiant may be glowing at maximum expansion, a temporary behemoth moments away, in cosmic terms, from becoming something infinitely smaller but infinitely denser. In that collapse, the universe will once again demonstrate that extremes are fleeting, and that gravity, patient and relentless, always shapes the final outcome. By the time we reach this point in the story, something subtle has shifted. We began with a simple question: is there a larger star in the universe? But now we understand that the answer is not a name. It is not UY Scuti. It is not Stevenson 2-18. It is not a record etched permanently into cosmic history. It is a moving boundary, a threshold defined by physics, environment, and time. To understand that boundary more deeply, we must examine the final constraint placed on stellar size, the relationship between luminosity and stability. Every star exists in a delicate equilibrium. Gravity pulls inward, pressure pushes outward. For most of a star's life, that balance is steady. But in the most massive stars, that balance becomes strained because radiation pressure grows increasingly important. Radiation is not passive. In extremely luminous stars, photons streaming outward from the core exert significant force on the outer layers. This force is not negligible. It competes directly with gravity. At a certain luminosity, the Eddington luminosity, radiation pressure equals gravitational attraction at the surface. If a star exceeds this limit, the outer layers can no longer remain gravitationally bound. They are pushed away. In the largest stars, luminosity approaches this critical threshold. They do not always exceed it permanently, but they hover near it. This proximity explains why hypergiants exhibit such strong stellar winds. They are almost tearing themselves apart. If a star tries to grow even larger, if its core processes increase luminosity further, the radiation-driven mass loss intensifies. The star sheds its outer layers faster. Expansion triggers erosion. Erosion limits expansion. This feedback loop acts like a governor, preventing indefinite growth, which means the larger stars are not limited by imagination. They are limited by physics. The universe does not allow a star to expand arbitrarily because the mechanisms that inflate it also destabilize it. This understanding changes how we think about the largest star. There may not be a single cosmic champion that exceeds all others by orders of magnitude. Instead, there may be a narrow range of maximum radii allowed by stellar structure, somewhere between roughly 1,500 and 2,500 solar radii. Instability becomes overwhelming. Beyond that, mass loss accelerates dramatically. The star cannot maintain equilibrium, and so the ceiling for stellar size may be more uniform across the universe than we expect. But there is another twist. Binary systems can complicate this limit. In a close binary, mass transfer can temporarily increase the mass and luminosity of one star. If a hypergiant gains additional mass from a companion, it might briefly approach more extreme conditions. However, this also increases instability. The enhanced luminosity drives stronger winds. In some cases, binary interaction leads not to larger stable stars, but to mergers or explosive outcomes. And then there are eruptive variables like Eta Carinae. In the 19th century, Eta Carinae underwent a massive outburst, ejecting several solar masses of material and briefly becoming one of the brightest stars in the sky. During such eruptions, the star's apparent radius can increase dramatically as the photosphere moves outward into the expanding material. But this is not stable expansion. It is temporary inflation. After the eruption subsides, the structure changes again. This reveals another key truth. A star's size depends on how we measure it and at what moment. During quiescence, a hypergiant may measure 1,500 solar radii. During eruption, its effective photosphere may extend much further. Are we measuring the core-supported radius or the temporarily inflated envelope? The difference matters. And so, the largest star may not be a single object. It may be a phase, a moment when stellar structure crosses into maximum extension before collapse, which brings us to the ultimate fate of these behemoths. When core collapse begins, the outer layers do not shrink gently. They fall inward violently. Shock waves propagate outward. Nuclear reactions run away. In a supernova, the entire extended envelope is expelled. The vast radius, billions of kilometers across, disappears in an explosion lasting weeks or months. The star's identity as a giant is erased. In its place remains something astonishingly compact. A neutron star only 20 kilometers wide, or a black hole whose event horizon may span only tens of kilometers. The transition from maximum extension to extreme compression is one of the most dramatic contrasts in physics. It is the universe's way of reminding us that size is not permanence, expansion is temporary, gravity is final, and yet the death of a hypergiant is not an ending. The expelled material enriches the interstellar medium. Heavy elements mix with gas clouds. New stars form from that enriched material. Some of those stars will be small and long-lived. Others may grow massive. A few may expand into hypergiants again. The cycle continues. And within that cycle lies another insight. The universe does not aim to produce the largest star possible. It aims to produce stars within physical constraints. Those constraints allow hypergiants to exist, but not to dominate indefinitely, which means that the largest star in the universe is not a singular triumph. It is an expression of limits, a balancing act between fusion and gravity, between radiation and mass, between expansion and erosion. And when we search the sky for behemoths, what we are really searching for is the edge of that balance. Somewhere, perhaps in a distant galaxy, undergoing intense star formation, a hypergiant may currently be near that edge. It may be thousands of times the sun's radius. It may be shedding material in powerful winds. Its core may be burning heavier elements at an accelerating pace. And in a few thousand years, a blink in cosmic time, it may collapse. If we could observe it across millions of years, we would see it swell, destabilize, and vanish. And then, in the remnants of its explosion, new stars would form, some modest, some massive. Perhaps one day, another hypergiant will briefly surpass its predecessor in radius. For a moment, it will be the largest star in the universe. And then, gravity will reclaim it. The title will pass. Not because the universe keeps a record, but because the physics of stars ensures that extremes are fleeting. In the end, the largest stars are not monuments to permanence. They are luminous thresholds, moments when the universe pushes structure to its limits and then transforms it into something entirely different. By now, we understand that the largest stars in the universe are not static monuments. They are dynamic, unstable, transitional phases in stellar evolution. But there is still one deeper layer to explore, one that ties together everything we have discussed. The largest stars are not simply big, they are inefficient. That may sound counterintuitive. After all, they shine with extraordinary brightness. They dominate their surroundings. They forge heavy elements. They shape galaxies. But in terms of longevity and balance, they are wasteful. A red dwarf, barely a fraction of the sun's mass, can burn steadily for trillions of years. It sips its hydrogen slowly. It remains stable. It wastes nothing. A hypergiant, by contrast, burns through its fuel with ferocious speed. It radiates enormous energy. It loses mass in violent winds. It expands dramatically, and it collapses after only a few million years. In cosmic terms, that is almost nothing. The largest stars live fast and die young. And that reveals something profound about scale and efficiency. Nature does not reward excess with permanence. In fact, the more massive and luminous a star becomes, the more unstable it tends to be. Fusion rates scale steeply with mass. A star twice as massive as another does not burn fuel twice as fast. It may burn it many times faster. The larger the star, the shorter its life. So the largest stars represent extremes not only of size, but of tempo, They are cosmic accelerations. They race through evolutionary stages that smaller stars move through slowly. Hydrogen burning ends quickly. Helium burning follows. Carbon, neon, oxygen, silicon. Each stage becomes shorter. In the final days of a hypergiant's life, silicon burning may last mere days before iron accumulates in the core, and then collapse. Which means that if we imagine the universe as a vast stage play, hypergiants are dramatic but brief characters. They enter brightly. They dominate the scene. They exit violently. But the quieter stars, the modest ones, remain long after. This contrast changes how we interpret largest. The largest star is not the most enduring. It is not the most stable. It is not the most common. It is a peak, an extreme condition reached when certain parameters align. And those parameters include mass, composition, rotation, environment, and time. Consider again the idea that the earlier stars may have been more massive than modern ones. If primordial stars truly reached hundreds or even thousands of solar masses, they likely burned so rapidly that none survive beyond a few million years. We cannot see them directly. They are long gone. But their remnants may remain as unusually massive black holes. This means the largest stars in cosmic history may not exist anymore. The record holder may be extinct. And if that is true, then the question, is this the largest star in the universe, becomes even more complex. Because the answer depends on when. Right now, in the observable universe as we see it today, or at any time in cosmic history. The distinction matters. The universe is nearly 14 billion years old. Stars have been forming and dying throughout that entire span. It would be statistically improbable for the largest star ever formed to still exist. It likely lived early. It likely died quickly. And its light may have faded long ago. Which brings us to another humbling realization. Our knowledge of extremes is always incomplete. We observe only what light reveals to us within a limited window of time. We reconstruct history from remnants, from supernovae, from black holes, from enriched gas clouds. The largest stars may have left behind the seeds of supermassive black holes at the centers of galaxies. In that sense, the behemoths of the early universe may have shaped cosmic architecture on scales far beyond their own. The largest star may not simply be a curiosity. It may have been a catalyst. And yet, even with this grand perspective, we return to the physics of limits. There is a maximum mass beyond which stars cannot remain stable. There is a maximum luminosity beyond which radiation strips mass faster than gravity can retain it. There is a maximum radius beyond which expansion triggers rapid loss. These limits are not arbitrary. They arise from fundamental constants: gravity, the speed of light, nuclear reaction rates, opacity. Which means that somewhere, embedded in the laws of physics themselves, lies the answer to how large a star can truly become. Not infinitely large, not arbitrarily vast, but within a range. And that range appears to top out at a few thousand times the sun's radius for red hypergiants under current cosmic conditions. Perhaps slightly more in rare environments, perhaps slightly less in metal-rich regions, but not tens of thousands, not millions. The universe is vast, but its laws are consistent, and so the largest stars represent the outer edge of what those laws allow. They are the universe stretching matter and energy to near breaking, but not beyond. And when they collapse, they remind us of another truth. Compression can exceed expansion. a hypergiant thousands of times, the Sun's radius can leave behind a black hole whose event horizon is smaller than a city. From the largest luminous spheres to invisible singularities, the arc of stellar evolution bends toward density, toward gravity, toward collapse. And perhaps that is the final lesson of the largest stars. They are not monuments to growth. They are preludes to transformation. They exist briefly at the edge of balance, glowing, unstable, immense, before gravity writes the final line. And somewhere in a distant cluster, at this very moment, a hypergiant may be swelling toward its maximum size. It may hold the title for now, but titles mean little to physics. The core is burning heavier elements. The clock is ticking, and gravity is patient. When the collapse comes, the largest star will vanish, and the search will begin again. Not for a permanent champion, but for the next star pushing against the limits of what the universe permits. By the time we arrive at the end of this journey, the original question feels different. Is this the largest star in the universe? At first, it sounded like a competition, a record, a single object standing above all others in a clear hierarchy of scale. But now we understand something deeper. The largest star is not a fixed title. It is a moving boundary, the outer edge of what gravity and radiation allow at any given moment in cosmic history. And that boundary is shaped by laws that are universal. Stars are born from collapse. They ignite fusion. They balance gravity with pressure. They evolve through stages. They swell. They destabilize. They collapse again. The largest stars represent the most extreme expression of that cycle. They are the moment when expansion reaches its peak. But peak does not mean permanence. The red hypergiant phase, where radius can exceed 1,500 or even 2,000 times that of the Sun, is short-lived. The star's outer layers are tenuous and unstable. Mass loss accelerates. Radiation pressure strains against gravity. Convection churns violently across surfaces that stretch billions of kilometers. And beneath that enormous envelope, something else is happening. The core is shrinking. Fusion is shifting to heavier elements. The clock is accelerating. The irony is striking. The larger the star becomes on the outside, the closer it is to collapse on the inside. Expansion is a sign of instability, not dominance. When iron accumulates in the core, fusion can no longer provide outward pressure. Gravity, which has been held back for millions of years, suddenly reclaims authority. In less than a second, the core implodes. Shockwaves surge outward. The vast, extended envelope, the very structure that made the star a behemoth, is blown into space in a supernova. The larger stars do not shrink gradually. They vanish explosively. And what remains is something radically different. A neutron star, only tens of kilometers across, containing more mass than the Sun. Or a black hole, an object whose event horizon might fit inside a small city, from billions of kilometers in radius to tens of kilometers in diameter. The transformation is almost incomprehensible. The largest luminous object becomes one of the smallest stellar remnants, and in that compression lies the final paradox. Size is temporary, density endures. The universe allows matter to expand dramatically, but it ultimately favors gravity's pull inward. The most massive stars create the most compact remnants. The behemoth becomes a singularity. Yet the story does not end there. The supernova explosion that marks the death of a hypergiant does not erase its influence. It enriches the surrounding space with heavy elements: carbon, oxygen, silicon, iron. The ingredients of planets and life are scattered across light years. Shockwaves compress nearby gas clouds, triggering new star formation. The death of the largest stars seeds the birth of future generations. Some of those stars will be modest, stable, and long-lived. Others may grow massive again. A few may swell into hypergiants, and perhaps one of them will briefly become larger than any currently known star. But even that new champion will be temporary. This cycle reveals something fundamental about the universe. There is no final largest star. There is only the current limit. And that limit is defined not by imagination, but by physics. Radiation pressure sets a ceiling on luminosity. Mass loss regulates expansion. Gravity ensures collapse. These forces do not compete randomly. They operate within equations that govern every star, in every galaxy, across cosmic time, which means that even if we discover a star slightly larger than Stephenson 2-18, the increase will not be infinite. It will be incremental, because the boundary is real. Somewhere between fusion and radiation pressure, between binding energy and mass loss, lies the maximum stable configuration for a star in our universe. We may refine its value. We may observe new candidates, but we will not escape the constraint. And perhaps that is the most profound conclusion. The universe is capable of staggering extremes, stars that could engulf our entire solar system, yet it operates within consistent laws. The largest stars are not exceptions to those laws. They are demonstrations of them. They show us how far matter can stretch before instability intervenes. They show us what happens when energy production peaks. They show us that expansion is never permanent, and in doing so, they also provide perspective. Our sun, modest and stable, may not hold any record for size, but its quiet longevity makes it more hospitable than any hypergiant. The largest stars are magnificent, but they are not nurturing. They are brilliant, but brief. They are giants, but fragile. And somewhere, right now, in a distant cluster, we may never resolve clearly. A red hypergiant may be swelling toward its maximum radius, its outer layers drifting, its core burning silicon, its lifespan measured in thousands of years. For this moment, it may be the largest star in existence, but gravity is patient, fusion is finite, and collapse is inevitable. The behemoth will fall, the envelope will explode, the remnant will shrink into something dense and dark, and the universe will continue, not with a single permanent champion, but with an endless sequence of giants rising to the limit and then yielding to the laws that govern them all. So is there a largest star in the universe? Perhaps, for now. But in a cosmos shaped by gravity and time, even the greatest giants are only passing phases in a much larger story.